So we're going to move to our second kind of keynote discussion. And I'm going to ask for a little help introducing the team from USC. I'm going to say this time last year, we had a keynote with Dr. Gary Michelson. And I remember being wowed by Gary in the work, his own creativity and his incredible innovation. And for those of you who weren't here last year, before I have Gary come up, I want to mention a few statistics around his own work. So Gary holds more than 1,000 patents. So if you guys think you're pretty hot shit because you have a few patents, wait till Gary comes up here and whips out his 1,000 patents, which is incredible. He's the founder and co-chair of Michelson Philanthropies, is one of our collaborators and supporters. Dr. Michelson is one of the most prolific inventors in history of medicine. I guess with 1,000 patents, you'd probably qualify. Congratulations on that. He's been inducted to both the National Inventors Hall of Fame as well as the National Academy of Inventors. I did want to mention he's playing a lead role in the establishment of the California Institute for Immunology here in Los Angeles. And I think that could be transformational, not just in terms of immunology, but also what's happening in biotech in California and worldwide. As I mentioned, Gary gave the keynote last year about his journey and the importance of developing and protecting intellectual property. So I'm going to ask Gary to come up and maybe set the stage for our next keynote, which will be a discussion from the Michelson Center for Convergent Bioscience. So Gary, you want to come up and join me for a few minutes?
I'd like for everybody in their own mind to just think about some great American action hero, male, female, doesn't matter, and think about the role they played in whatever it was, a movie or TV program. And the principle is, it really doesn't matter whether the posse does or does not come at the end. The action hero always stands alone. He's already done whatever the hard work is. Think about that for a minute. The problem is that in science, that is the problem. That's the problem. And the reason that problem exists is that in this country at this time, the lead funder for all academic medical research is the NIH. And they don't fund team research. They fund individual researchers. And I don't want to tell you that that model doesn't work. It just doesn't work well. And here's the problem. People are not smarter today than our grandparents were or their grandparents. What's happened is the amount of knowledge in the world has expanded, and it's expanding at an ever increasing rate. So what that means is that people today know more and more about less and less. And I would invite anybody to tour any university campus in this country, and you'll see a chemistry building, and you'll see a biology building, and you'll see an engineering building. It's worse. It's worse than the fact that the information is getting compartmentalized, so are the people. Now, I've said this before, for better or worse, like it or don't like it, one of the most successful projects of all time was the Manhattan Project. What they did in record time is much like what JPL did. And they had, just like this JPL story, they had nuclear physicists, electrical engineers, mechanical engineers, welders, machinists, all these people came to work every day and they worked on just one thing. And they had a goal. That's the way that science needs to be done today. We need to bring silo these people, bring them out of their buildings, have them eat, sleep, and work together on a project. And the way I look at this is, there's nobody smarter than the person you're gonna hear from next. But it's like walking in to a Las Vegas casino and putting all your money on one number on the roulette wheel. For me, I'd rather have 20 people working on a project and we'll put our money on black or red. You're just gonna win more often. And so, what are we talking about? Well, I don't know about the girls, but the boys in this room, we all had magnifying glasses when we were kids and we were starting fires. Anybody here not start a fire? I mean, we had these magnifying glasses, and what you were doing is you're just taking these parallel rays of the sun and you're focusing them on a point. And that's what we need to be doing in science. So the name that people like Scott and I gave this to was Convergent Science, where you take all these parallel rays and you converge them. And what's really interesting is If somebody were to say to me, what do you think the most powerful innovation in all science has been in recent time? It's clearly big data. Big data is rocking the world. The problem is, without the people who know how to process that and derive the meaning, it's like sucking on a fire hose. Just blow your head off. So you need the deep machine learning, you need the AI, you need the pattern recognition, and you need these people that know how to derive the meaning from the data. Well, they're up in their own building. It's called computational sciences. They're not talking to the molecular biologists. What we need to do is de-silo all those people, put them together, and give them a project to work on. And the person you're going to hear from next, that's what he does. He's one of the people that persuaded me to jump into this with him. So Scott, where are you hiding? Come on, come on.
I'm going to call a panel up. I do want to introduce, and thank you, Gary, for that. We are drinking the same Kool-Aid because I think of our work at the Alliance to build an ecosystem is very similarly aligned. You can have great universities and entrepreneurs and venture capitalists and community-based organizations, but the productivity of those individual elements are nothing like when they work together as a connected system. So our work at the Alliance is very similar to the convergence work that I think we're going to hear about shortly. So I'm going to introduce Debbie Lind, and then I'm going to ask her, and I ask the rest of the panelists to come up. Debbie has agreed to be our moderator for this group. Debbie has become a great not yet, hold on. She's enthusiastic. That's going to say about Debbie. She's very enthusiastic. She's the VP of Partnerships at Caris Life Sciences, which is a leader in personalized medicine. Debbie is an expert in strategy, business development, and venture capital in healthcare and med devices. Previously, she had roles at Boehringer Ingelheim and was the executive director of their venture fund. She's an adjunct faculty at UCLA and has a Ph.D. in bioinformatics from UCSF and a master's degree in engineering from Stanford. So I figured, she's going to really challenge you guys today. So Debbie, come up, and can we have the panel from USC come join us as well?
Wonderful. Thrilled to be here and to be able to moderate this distinguished set of speakers. We talked about the siloed nature of science, and we have next a discussion on a center situated here in Los Angeles with an amazing hospital system, an amazing academic center, a school, engineering school that basically stitches all of these superheroes together to work together. So we're going to hear about the structure of how it's set up, the processes, and how you all foster collaboration. So Scott, would you like to tell us a little bit about the structure of the center and introduce yourself a little bit?
So I'm Scott Fraser. I joined USC a few years ago after spending a quarter century at Caltech. What we've been involved in is the first purpose-built Convergent Science Center. Many of us have talked about convergent science and about interdisciplinary science. And as Gary mentioned, we've been very good at building silos and separating things into individual little pegs and boxes. The goal of our center is to really break from that and to really start bringing together the different disciplines. And it's built upon some of the principles that we learned both from inside and outside. So it's built from many of the things we did right and even more of the things we did wrong when I was at Caltech. It also is built on many of the things that Gary and others offered to us as advice. I mean, Gary offered us much, much more than financial support for building the Convergent Science Center. He pointed out some best practices that we needed to use to foster innovation. And it's interesting that he would bring up a roulette wheel because really innovation is a lot of chance. And it's trying to harvest accidents. It's not, you don't sort of go up to somebody and say, well, maybe if you've got a challenge like making a ventilator in zero amount of time, which is just amazing. But it's hard to go up to somebody and say, innovate and invent something tomorrow. What instead is happening is we believe in convergent science that there's a bunch of accidental interactions, and those accidental interactions have to be harvested before they die of good intentions. And the way we used to build buildings, the theoretical physics building at Caltech, I think, is probably an excellent example. It was, if any of you have ever seen the movie Barton Fink, with the hallway that there was never anybody in it and all the doors were locked and it was the most impersonal hallway you could imagine, that felt like a warm place in comparison to the theoretical physics building. There was a whole array of locked and closed doors and a hallway that looked like it was built out of war surplus materials, and it probably was. And it caused no interaction at all. Its goal was to allow people to focus and compartmentalize. They remodeled that a few years ago, and it is now the most exciting building on campus, or one of the most exciting buildings, because there's, at every intersection, there's a chalkboard, there's a place to sit, there's a place to innovate and to bump into one another. And it turns accidental meetings into productive moments.
So Scott, walk me through, if I were to walk through the Convergent Center, Bioscience Center, what am I seeing? What am I looking at?
What you're seeing is a building that is a COVID practices nightmare, because what we built was a building that was meant to get people to bump into one another, for people to bump into one another and interact when they're having a headache or when they're having a success, and to brag to another person, something just worked, or something just worked, didn't work, or something's impossible. And every place that you could have that interaction, which of course we all had to stop doing for just a year and a half after we opened the center, so that was a challenge. There's whiteboards, there's places to sit, there's places to plug in your computer to the network, there's places to plug into a monitor. The idea is to not have any delay between the happenstance of us meeting and having a potential problem and a potential solution, and an ability to sit there and harvest it.
Excellent. Francesco, I'd love to hear a little bit about you, but also we were talking right before at lunchtime about you've got a nano fabrication device, you've got people doing genomics, you have computing folks. Tell us how that sort of infrastructure led to some successes that you've had.
Sure. So I'm Francesco Cutrale. I'm a research faculty in USC, but I'm also the CEO and co-founder of Kulia Labs, one of the startups that are coming out from the Michelson Center for Convergent Biosciences. Now, the center is amazing. It's a mix and match of multiple types of disciplines. It's a multidisciplinary environment, and that is unique. You have a nanofab center in the basement next to electron microscopes. You have a layer of a floor of people with the expertise in blood cell and circulating tumor cell analysis. You have chemists, you have physicists, you have biophysicists, you have an imaging center, you have people who design implantable device for brain, and you have people who design the most innovative AI architectures. Now, this is a very powerful environment. To follow up on Scott's comment, these random meetings or this random presentation that you bump into, you have events where engineers interact with biologists, and then the engineer discovers that the solution he has come up with is a solution to a problem that nobody has. Or you have a biologist that is working on a problem, and he realizes, thanks to the engineer, that his problem has been solved somewhere else, for example, in telecommunication 20 years ago, nominally for a different problem, but practically for a very, very, very similar issue. So this kind of mix and match of different aspects really is powerful tool for catalyzing and synergistically move forward the projects.
Can you give us an example of something that you had an aha moment and then kind of
Sure. So
along?
there's a tendency I sense in research, like Gary was mentioning earlier, to silo projects, do individual research. Now I believe, came up with an approach for speeding up the transition of projects from research into startups. And the idea is we need to follow whatever is a standard business model. We need to identify what is a a problem. We need to identify if there is a need to solve that problem. We need to find a solution. The solution needs to be amenable to a commercialization, needs to be improving, needs to be manufacturable, repeatable, and needs to be solving a lot of other issues. Now, some of these aspects belong to a startup phase of technology, but the initial aspects, we can define them within this center. And it's extremely powerful, but you cannot do it alone. You need to have this multidisciplinary environment. You need to discuss with people, you need to see different perspectives, because we believe that the most innovative ideas arise from the convergence of multiple disciplines. Once you are able to identify a problem that really addresses a need for multiple disciplines, then you have a really innovative tool.
And if I could amplify on it, part of the problem is all these things happen not by us mandating it from above. You shall talk to you. But the goal is to have it so that when you have the problem, the solution is nearby. Gary mentioned big data. Right next to the coffee machine is the lab that's the big data lab. Just next to them is the systems biology lab. The people that are in another one of the sort of crossroads is the AI lab. And so when you're walking by on your way to get coffee is when you're probably thinking about the problem that you haven't solved. Or that, basically that you're either super excited because something's worked or super depressed because something hasn't worked. And the big data people help you on both of them. So the idea is to almost do the same thing of trying to get lightning to strike somewhere by putting a lot of lightning rods around, not by suddenly organizing it like it's a military organization and ordering people to do certain things and have certain interactions. Just provide it so that by accident it happens and then we harvest it.
Excellent. And a specific invention might help the audience.
Sure. So one example is the technology that provided the basis for Kulia Labs. It's a set of 3 different analysis tools that were designed with the principle of identifying, visualizing, and separating very subtle color differences within images in order to provide scientists and practitioners with a tool that really empowers them with the identification of really invisible objects, making them visible. So let me give you an example. This is a founding block, basically. It's a basic technology. The idea is you can imagine you're able to observe a tissue and distinguish the different type of structures that are within it, right? That's extremely powerful. That's what we published, and we were all over the news with this. But then we tried to push this further. What if we could image the metabolism of cells? We would provide scientists, we would provide clinicians with something that is based on light, non-disruptive, real-time, that can really give you an assessment of relatively abnormal metabolic activities within tissues. And you have a huge body of knowledge in literature that says there is cancerous lesions that are known to have different metabolic activity. Well, that's perfect. But this is an example that really came from all these random discussions and events and encounters around the center.
And what's been interesting is that in experimental animals, we could do many of these things, but it means putting fluorescent proteins into them or indicators or whatever. Very few patients come in with GFP integrated into their cells to report on something. What it turns out is that the same tools we are using for analyzing the things in my lab to look at developing embryos worked in patients, and the cancer biologists and the diabetes clinicians both had the problem of wanting to look at patient-derived samples. So this tool of being able to look at the metabolism, invisible differences basically made visible that let you eavesdrop on the metabolism of the cells, is letting us see therapeutic targets. It's letting us see cancer stem cells. It's letting us understand type 2 diabetes. And it's doing it for free. And the really weird thing is that the signal that we're seeing in live patients, we can also find in archival things that are in pathology archives that were fixed 10 years ago. That invisible signal is there in the slides as well. So some of the people at Children's Hospital are now tolling through some of the old pathology slides and are able to reinterpret on what the physiology was of that sample when it was alive in a patient based on what it's doing coming off the shelf 10 years later.
So
Yeah.
future forward, this is
Mhm.
going to be in real time. So it's not backwards in time, which is what we're kind of doing now, but we're going to be doing this real time future forward. So if you think about slides, you know, when a cancer patient has a biopsy and this is put on a slide, a tissue, a part of the tissue is put on a slide, that was the past. And now it's going to be 3D, but real time into the future with optical imaging kind of built onto that, so you could see progression, metabolism, all sorts of things. So that's
In the
incredible.
person without a knife.
In the person without a knife.
In a few minutes.
And with a telepathology pathologist telling you what to do right away. So
Right.
you kind of hit on a couple of elements, which is optics, imaging, biology, you know, obviously medicine. And I know that you have a film school nearby, and so this cross-fertilization of engineering to filmmaking, which is obviously uses images and optics and colors and all sorts of things. Can you tell us a little bit maybe about how you've maybe
Well, we have
cross-fertilized
two
there?
examples where we've hijacked things from the cinema school. So we're used to thinking about the cinema school as a consumer of computer graphics and things of that sort. There's a lot of, like Avatar came out, the technology for doing that came out of USC, and similarly with Minority Report and several others. Few of the things came out of Caltech's computer graphics labs. But the thing that cinema is really good at doing is telling stories and making an immersive environment and transporting you to another world. And so one of the things we're doing now with this multidimensional data that is really pretty daunting to try to get a grip on is working with the storytellers in the World Building Media Lab and having them make immersive ways of interacting with the data. They're building us tools now that we're using in everywhere from the K through 12 classroom to the research lab to try to look at complex events like cell signaling cascades. I don't know how many of you have ever looked at like growth factors and the way they work, but it's like the same receptors talk to a bazillion different things and all. It is daunting to try to get a grip on it if you think it works like a light switch on the wall that turns on the lights up above. It doesn't work that way. It's a network of interactions in different contexts, temporally and spatially. A cinema solution to that works. And once you put the goggles on, we've got an immersive environment that called World in a Cell right now that allows you to interrogate some of those things. So this is an aspect of using the sort of storytelling part of cinema. Francesco has been involved in making other tools that again steals liberally from the cinema world.
Yes. Some interactions that we had. So most of the data that we work with is multidimensional data. Imagine you could see a three-dimensional data set and you want to interact with it. You want to understand how cells are evolving over time, how cells are interacting one with the other within a tissue. It's pretty complicated because in general, monitors are two-dimensional. And sometimes it's easy to do comparison between three-dimensional data sets. So what we had worked with a cinema school was a solution based on virtual reality that would create and render these very large data sets beyond the capability of normal computers, but done so modularly that would allow scientists to work across the continent on the same three-dimensional data set, to look at the same three-dimensional data set across the web into this virtual room and to discuss together about the results of the science.
So that means sort of converting something from data analysis, being the sole person looking at the piece of data and waiting for the lightning bolt to strike them, to something that really fosters collaboration and allows multiple people to live in that same virtual multidimensional space and be able to each contribute together and trying to interpret it.
That's incredible. I think of a ChatGPT for biobiology or bioscience. The way you're describing this is interpretable and all of that. I wanted to ask one last question as we're probably closing soon. Principles for how you work together. I imagine this is quite chaotic if a lot of people are kind of working together on a problem from different disciplines. How do you kind of think about principles for organizing and structuring and how you work together?
Well, it is like herding the cats. And so the way we do it, though, is by making things that are natural attractors. I mean, we probably have 3 or 4 dozen patents out of our espresso machine, just because having a free espresso machine pulls people together either at their best or their worst moment to complain or to gloat about a new finding or a new obstacle. That other thing is that the building is built around cores. And cores are way more than a set of tools that are sitting in a room. It's a whole bunch of expertise, and it's a whole bunch of foot traffic into and out of the core, and knowledge flow into and out of the core. So the fact that Francesco can do what he does with visualizing and seeing specimens means that people are coming in and bumping into one another, not because I'm ordaining it, but because their own selfish motives are bringing them in, and they bump into other people that either want to work with his tools or to steal his coffee. So how is it working? Well, just in the 4th floor, the little bit of the building that we work in, I think we are up to, since 2017, the 13th startup that's come out of it. So that's 1 floor of 1 building. That's an order of magnitude more than the total of the things that came out of the Beckman Institute during the quarter century I was there. And that's adding up all the floors and many more years, and with no pandemic. So I'd say that this thing of just engineering accidents and bringing people together so that they were rewarding them with their own selfish motives to interact and to find solutions has had a good payoff.
Yeah, I think it's also true that we are fostering an environment of collaboration and open atmosphere where people can share their ideas and freely contribute, where junior students and lead innovators can work together and harness this power of this cooperation to create ideas that are borderline science fiction. And I think one example could be this latest work we have been working on that really takes the idea from the Star Trek tricorder, and we decided to build one of these. And we created a classroom, a new type of machine learning architecture that works on it, where we have teacher machine learning machines, student machine learning machines, and all of these work together. And now you can just shine light on the skin of somebody, and you can obtain a 3-dimensional data set of their information up to 5 millimeters below the skin. And this was unthinkable unless you were looking at Star Trek as much as I did. But the collaboration and the integration of multiple ideas really brought this together. And it sounds science fiction, but it's really extremely scientific grounded. There is a logic behind. There is photomigration. There is a lot of aspects of this that we have taught the machines. But this would have not come together unless we had biologists, unless we had a number of physicists, biophysicists, and AI experts within the same environment. And this was, again, accidental meetings that progressed into something that is borderline extraordinary.
Yeah, so Star Trek in the original Italian is a lot more decisive on these matters. But it has been fun to try to deal with the things that people think are impossible or impractical. I mean, 5 millimeters isn't going all the way through the person yet, but it's many millimeters below the surface of where we thought we could get just a year or 2 ago. And it's been fascinating watching as these different disciplines converge together and get solutions that we didn't even think we could get to just a little while ago.
That's incredible. I mean, we just heard about going from idea to FDA in 37 days, and now we have a center that fosters all of this. So how many innovations can we spin out if we have a 37-day urgent timeline throughout the center?
I hope we're motivated, but not that motivated by pandemic and colleagues dying. But it is really powerful to think about how this model of bringing together the different disciplines and the different people. And I have to say, you know, in some ways it's giving up a little bit of your ego, but the payoff has been so much greater that in fact it's even more gratifying than being the sole investigator with the sole NIH grant in your sole lab. And that's what's been so fun about it.
Yeah, I can feel the energy and the passion and the excitement, and speaking from own experience, it's so much better to do this in a community than to do it by yourself. So I invite myself to go steal some of your coffee and hang out with you all, and probably
anybody that
everybody
wants to come
can come.
we love hearing about problems. We love hearing about solutions we don't know about. And I can say that both at USC and when we're at Caltech, we scared the daylights out of many of the other faculty because they're used to people just saying, oh yes, whatever you say is true. We, in fact, will pepper them with questions and interrogate it and find out the limits of where it's true. And that's where the real opportunities are. So this dynamic tension between questioning and all. So if you're willing to come and steal our coffee and willing to field our questions, any of you can come to the lab and interact. And what we're hoping to do is to make the cores available to the community at large so that in fact it can help build a sort of alliance that the local biotech community and tech community in general can build upon, because the cores are meant to be this sort of interchange mediator.
Well, with that said, thank you so much, both of you, for a tremendously interesting discussion, and we'll look forward to our visit.
Thank you.
Okay, thank you.
That was great. I made some notes of key takeaways. One is the value of free espresso machine. So maybe Starbucks needs to play a bigger role in our innovation economy. I do love this idea of getting lightning to strike by putting out more lightning rods. You know, that metaphor is really exciting, I think, for us in the innovation world, and the value of engineering accidents. Scott, if we had more time, I'd want to ask you about, in the tech world, not just bioscience and the wet lab research world, but with the pandemic, there's been a pretty significant decentralization of where work happens. And I'm curious about what the implications are for this convergent collaboration in a world where a lot of our innovation companies have kind of shed their workforce out of centralized locations where it's hard to gather around an espresso machine if someone's in Park City and someone else is in Colorado and someone's in Manhattan Beach. So I am concerned about that because I do think ultimately there could be a cost that it's hard for us to calculate, and we'll only know 20 years from now what maybe we know the benefits of remote work is people don't drive, and we see that, but the hidden costs are of decentralizing our innovators. I do think it's, you know, hopefully we'll figure that out sooner rather than later, but great discussion, and love the enthusiasm. And as somebody who's once again, this ecosystem building, the connectivity, I think is the secret sauce to innovation and problem solving, and we hope to provide a little bit of that here today. So that kind of wraps up kind of our main stage activities. We are going to go out to the 2 tracks, and so we'll be hearing from amazing spin-out companies. Let's see, the life science track, Steve, is in this room, I think, right? And the tech track is next door. So that should be exciting. I'll be bouncing back and forth, looking for mind-blowing innovation for myself. So I have a little scorecard. I do also want to thank again Wilson Sonsini, KPBB, JPL NASA, and Michelson Research for supporting us today. I know you're going to have an amazing afternoon of discussion and discovery and seeing great companies. So I look forward to connecting you with all of you during cocktail hour after that to hear what you learned today. And for those of you who are building innovation companies, good luck on stage and good luck in your journey. So we're going to transition to the breakout rooms. Thank you very much.